All right, so let's see. Let's get going. What we'll do is we have this room till about 7 o'clock, or maybe slightly after that as well. So we'll have a short break in the middle. I think it's a relatively long time, so maybe about a 5-minute break around 5:55 or 6-ish, and then I think the food and all are going to come in around 6:50, so we can kind of carry on till then. And after after the food arrives and all, I'll be around, and you can ask me questions and all that if you have questions about the homework, and so on. So I'll continue with that. So, okay. So what I want to do was, essentially, we are still kind of building up all the notions and quantitative as well as qualitative tools to address the problem of transport. And one of the things is we are trying to develop notions of if I know classical transport of particles in fields or force that experience forces, how do I find the quantum version of it, and how do we go about thinking through the problem and trying to get so how do you set up the problem is really what we're after. And we said that, as in the last class we discussed quite a bit about time independent Schrödinger equation is now necessary because of the wave particle duality, just to find the allowed energies of the electron or of any quantum state, any quantum particle. And then using the wave function, so I can find the entire spectrum of allowed energies for the particle in any given potential by solving that equation. And then I need to go to the dynamics. To understand the dynamics, I need to look at the time-dependent Schrödinger equation, and that is the prescription to find out the stationary states as well as all the dynamics of them under applied potentials and all that. So it's kind of that's the general strategy, right? And what we are doing now is we're looking at a few specific cases. Just like in classical mechanics, you look at throwing a ball down a hill, or mass spring systems. Just like you solve classical mechanics problems to look at dynamics of point masses or things like that. We are looking at the analogous things in the quantum version now. Right? That's what we are doing now. Inclined planes and all that stuff, right? That you solve for classical mechanics. Right? So the first thing we are looked at was this free electron picture, and then that helps us also calibrate that if I have a free electron and it has a certain energy, there's a wavelength associated with that energy, and wave vector and so on. If the kinetic energy is very large, then the wave vector k is large, and therefore the wavelength shrinks. So higher the kinetic energy, smaller the wavelength of the electron. And that's an important concept when we start looking at nanoscale devices. Many times you need the electron to enter a region which is only 5 nanometers wide, and then you know that it must have a certain energy to be able to fit in there. If it is very low energy, it cannot go in, the wavelength would be too long, and such things. So it's like electrons also, the wavelength of the electron becomes kind of tied to whether the electron is allowed in a region or not, and so on. So it will be reflected, you can't enter, and things like that. So you can imagine, as transistors have become very, very small now, this is a problem. You can't really push electrons into a 5 nanometer wide region. The transistor is very small. So this is actually an actual problem, and we are going to look at some of its manifestations in these nanoscale devices in the class today as well. Yeah. Okay, so I wanted to, just to kind of make sure that in preparation for the future, not so much what you're going to use today as much as a little bit in the future, I had said that for looking at all these allowed states of electrons, we can think of each state. Each state has its own, k, its own wave function, and its own energy, and so on. And we can think of each of these states as a vector. That's what I was saying. As we can picture it as a vector. So a state for the free electron energies. A state here or a state there. That's K1. That's K2. And we, for that notation, we use this Dirac notation with a put them inside these brackets, and so that we are going to picture as a vector in some vector space. It is analogous to a vector in your three-dimensional space. It's analogous, but it's not the same, right? And so let's say in 3D space we have a vector something like that, and in this new space, which is what we're going to call, again, these things are somewhat abstract, but it's not necessarily, I think it will make sense once we start looking, why are we doing this, it should make sense. So you can imagine this state of the electron, this quantum state of the electron as a vector in a Hilbert space here, which is pointing in certain direction, and that state as another vector that's pointing in some other direction, right, and so on. Now, one of the things is what's very interesting is if you have two states like this and both are stationary states, both are allowed eigenvalues of your Schrodinger equation. If I take psi, the wave function of state K1 as a function of x, I multiply it with a complex conjugate of wave function of this state, right? And then I integrate it over all space, I will get what? You get a 0 if they are different. And this is a very interesting property of eigenvalues of any equation of Schrodinger equation type, right? It's a mathematically guaranteed. You'll get a 0, or in other words, you get, if K1 and K2 are the same, you get a 1, right? That's normalized. I mean, for free particles, not normalized. But if they are different, you get a 0. And so that's the Kronecker Delta symbol, right? Kronecker Delta symbol can take a value of 0 or 1. This is not the same as the other delta, which is the Dirac delta function. Okay? So 0 when K1 is not equal to K2, K1 is equal to K2. And this causes, if you are not comfortable with it, as soon as we start doing things like Fermi's golden rule and all that, we'll be needing the Dirac delta function too. So we should be very clear about a Kronecker delta. The answer is either 0 or 1. Dirac delta is continuous function. It can be 0, it can be infinity, it can be anything in between. So Dirac delta is a continuous function. This is the discrete version of it. It's a digital version of it, zeros and ones, right? Okay. So now you can see the reason it's called a Hilbert space instead of a 3D space or 4D space is because you have an infinite number of states here, and we have just found that any two states I choose are actually orthogonal to each other, meaning they're perpendicular, effectively, right? So now I can have the third one, K3, which is perpendicular to both of them, K4, and all of them. So this is, you can imagine why it's called, it's an infinite dimensional space, right? Each of these vectors is kind of one axis in that space, right? So that's why it's called an infinite dimensional vector space. And if you want to collect all these states, K1 at the bottom here, or K0 at the bottom, and all of them, that's another way to write or indicate this sort of a Kn and so on. This is the set of all these vectors or eigenstates, eigenvectors, eigenstates. It's all the same, really. Okay, so now just like any vector in your real space, be it this way, that way, you can write or decompose any vector as as a certain coefficient times x hat plus some coefficient times y hat plus some coefficient like times z hat, right? Just like you can get any vector like that. In the same way, any state of this free electron or any electron, in any potential well or any sort of quantum state, I can write it as a sum of k's, or let's choose a slightly different symbol, sum over i's of ci times ki, where ki's are these states. This is the same deal, right? in the 3D geometry, you have 3 unit vectors, x, y, and z. These are your bases. Here, this is your basis. Right? And when I'm writing this k, so the reason we want to imagine it as a vector in this abstract space is the following. Okay, so so I can take this vector and say, what is the projection of this vector? What is the length of this vector along the x direction or the y direction, right? So I can take this vector, and to find how long is the vector along the x direction, what I do is a dot product, right, along the x-axis. That'll give me a sub x. Right? It'll pull out this number. Right? How much strength does it have in the x direction? How much strength does it have in the y direction, z direction, and all that, right? If you're doing relativity, there is another axis which is time, so that's a 4D vector now, 4-dimensional vector, and then so on. And I think you can probably see that even physically, even in classical mechanics, you're actually in 4 dimensions. I mean, so there's time as well, right? So in quantum mechanics, it's going to infinite dimensions here, and in a very similar way, now instead of saying along the x direction, y direction, we can choose the 2 variables we have in which are of high importance for mechanics or the dynamics of particles, which is x and p, right? The location, length, and the momentum, right? So you can actually say, ask a question that what is the projection of this abstract vector, the vector. If the electron is in some sort of a mixed up state with certain coefficient, let me sketch these coefficients here. Okay, so I can cook up any sort of a state here by suitably choosing some weights of each of these states. So let's say I choose a weight of this much, and here, and maybe a weight of a little larger weight here, and then a little less weight here, and so I can kind of choose a distribution of c sub k's. Or c sub i's, let's say, okay? C sub i's. Right? I can choose some sort of thing there, right? And then I can construct a state which is a superposed state. It's not eigenstate anymore, right? Superposed states are a wave packet, something like that. So I can construct such a state, and that state will look something like this. You can also construct a completely pure eigenstate, in which case only one of these will be 1, all the rest would be 0, right? So that's a pure eigenstate, right? What I'm trying to say is now that whatever state I create like this here in this Hilbert space, it's obviously impossible to draw a diagram, but it will have some sort of a, it will be a vector which will be composed of a little bit of this, little bit of that, and all that, right? It's mixed up in this infinite dimensional space, right? But still, this is a vector, and this is sort of an abstract quantity at this point. But the moment I ask a question like, what is the so instead of writing it in this way, I will write it as, again, in this bracket notation. Okay, so bracket. So I can go in and ask now that you can obviously ask how much of the state is composed of K2, K1, and you'll get these other numbers, right? These are the coefficients of that state. But I can ask another question. For example, I can ask, if I take this vector in the Hilbert space, okay, and I project it onto real space. What is real space? Now, real space is x, y, and z, for example. I can project it into real space and ask, what is this inner product, or what is this dot product version of Hilbert space state vector and a real space state vector? Right? These are state vectors real space. So that is what we actually write. And when so I'm saying this is x is a notation. It can be r. So I'm going to project this state onto real space. This is equivalent to the dot product here. And this is what we call as the wave function of the particle psi of x. This is the function that we get. So we are, this is how it connects to the Hilbert space. And so I can also project it onto the momentum space, okay, and write it as psi p. It can have a x, dependence, or it can also have a momentum dependence here. In fact, I think for the free electron, it is going to have a momentum dependence too, right? But so these are you can think of them also as projections. Look at in that direction, okay? Any questions here? I just want to pause a little. again, hopefully as we start using this, it'll become clearer, if you haven't seen this before, but at least, this is, all right, so let's look at an example of how this would kind of work out. So instead of being completely free along a line, we can put it on a ring. So this is called a periodic condition or periodic boundary condition. And this ring can be extremely large, in which case it's effectively like a long length. And in which case now what you get immediately is the moment we put an electron on a ring, this state of continuous number eigenvalues will not be allowed anymore. There will be only discrete eigenvalues allowed. And I think you can see right away, I'll kind of assume that you have done some reading about this, that the wave function is a single valued function. If I have a wave function of some value here, and I go around, and the wave function can wiggle all at once, but when I come back here, it should come back to the same value. So that requirement itself, that is the classic wave fitting requirement. All quantization occurs because of this reason, because the state of the particle is unique. The wave function must be a single valued function, for example. Mathematically, that's how it captures. So if I oscillate around and I come back, it should come back to the sthink value. I think I was trying to sketch that here, but that's fine. Yeah. And therefore, the wave function, as a function of x, I think you can see that you can think of it as r theta or x here as you go around. And when you come back with a length L, it should come back to itself. And if I choose my trial wave function for this state was e to the power I kx, then it's pretty clear that e to the power I kx plus L must come back to itself, right? It must be that. And it's true for all x, no matter where you start. So as a result, you must have that IKL must be equal to 1, and therefore you can see right away that not all k's are allowed anymore. For any given length, there are only certain k's that are allowed, and such that k times L must be equal to 2 pi times an integer, right? Because that's e to the power I 2 pi times an integer, right? And also, as we're looking at this, there's another way, another picture you can have in mind, which may not be very helpful right now, but it will become very helpful later, is as the particle is moving around on a ring, right? As the electron, let's say, is moving around on a ring, and if my wave function is is e to the power I kx, for example, as the x changes, e to the power I kx is e to the power I theta on a complex plane. So if I took real part of the wave function and the imaginary part of the wave function, so what it's doing is it's traversing a circle, right, on the complex plane here, right? As you move along x, it's going and it's traversing a circle on the complex plane, the wave function itself, right? Yeah. And later on, we'll see that when we have lots of particles with different k's, you can see why the k will determine the phase. So if you translate something with larger k or a shorter wavelength or larger energy, then you circle faster, or meaning with a smaller x. So that's why k is 2 pi by the wavelength, right? And x is obviously x. So you can see that I mean, this is nothing new really. I mean, it's true for all waves, but even the quantum state it's doing it's traversing this in the imaginary. So just to kind of keep in mind, become important later. Yeah. Okay, so here we just get that it must be this, and therefore not all k's are allowed because your L is clamped, the length, you fix the length of the ring, and therefore k becomes quantized. Only ends of so 0 is actually allowed, 1, 2, and so on. All these are allowed, right? 0 is also allowed, and kn becomes 2 pi over the length of the ring, the circumference of the ring times an integer, right? So, yeah. Where n is again 0, 1, 2, 3, all that. So n is 0 is actually allowed here, and that's important to realize. This is not really the particle in a box that where you have what you call as the ground state energy, but here it is allowed. In fact, you can tell me if n is equal to 0, how will the wave function look? I want to sketch the wave function around the ring. How will it look? So when n is equal to 0, kn is 0, right? And therefore e to the power ikx is,
a constant all the way?
It's a constant, right? E to the power I times 0 is 1, right? So it's actually the wave function of the particle for n is equal to 0 is just a constant. It just goes around, like that. It doesn't change at all as the particle goes around, right? Does that make sense? I mean, I'm sketching the wave function. As you can imagine, I could do that only for this situation. But the moment I go to n is equal to 1, it's a complex value, so you have to plot separately the real part and the imaginary part and all that. But regardless, that's here n is equal to 0. N is equal to 1. What will happen then? Actually, the number n is a count of the number of nodes of the wave function, how many times it goes through 0, right? The wave function starts with some finite value and goes through 0. So n is equal to 1 would be when it completes. So again, it can start somewhere, but it has to go around. It's actually going to be difficult for me to sketch, but it has to go through 0, then go negative, and maybe come back up. I think so it'll go to 0, and then come back up here somehow. So anyway, it's hard. And then as you increase the n is equal to 1 and 2, it'll go. It'll cut through 0 multiple times now, right? And so it starts, kind of becoming more and more oscillatory as you increase. So, yeah. Okay. Yeah.
In the equation for the wave function, there's nothing that really specifies the path it's taking. This state is path independent, right?
You mean?
Like it being a circle, it doesn't have to be a circle.
Okay, so physically, clearly, this is not going in a circle because then you must have y as well, right? X, y, and all that. So this is the way it's created. This is artificial model saying that we have a very large, very large ring, and any small part of it looks linear. But when we do magnetic fields later, this becomes real. Where you have a x, y, and the electron actually is doing cyclotron orbits, then it will be actually very real. But at this point, it's created. This is a way to introduce this finite length into the picture. Where you can normalize the wave function now, and that's one of the things I wanted to get to right now. So the wave function is normalized now. Instead of being the length being the circumference being infinite, you have a certain finite circumference, and therefore I can write now that the nth wave function you can show that it will have a normalization coefficient of this 1 over square root of length times 2 pi by this times x. That's your wave function for the nth state here. So n is equal to 0 is here. N is equal to 1, 2, 3, and 4, and the separation between any two states, and this is again a very important quantity, though it's trivial, but you can see that kn is an integer times 2 pi by L, so n plus 1 minus n is the separation is just 2 pi by L, 2 pi by the length of the whole region, so, and 2 pi over L, right? And therefore you can find what's the separation in energy and all that sort of thing, right? So. All right. So the energy expression stays exactly the same, really, right? But I think the only one of the new things here is you got your wave function is normalized. So when you can see right away that if I take mod square of this becomes just 1, and when I have to integrate it from 0 to L, I just have to integrate 1 over L times integral of dx from 0 to L, so that's 1. So essentially it has to be 1 over square root of length as the normalization factor. Though the wave function is, excuse me, though the wave function, the real and the imaginary parts are changing in space, the absolute value is not changing in space. It's actually constant. The absolute value, right? Mod of the psi. For any n state, okay. So the wave function, we said that n is equal to 0, the wave function is constant. But actually, if you ask the amplitude of the function, absolute value, that's constant for all n's, not just for 0, for 1, 2, 3, all of them. It's constant. So even for all of them, mod psi square or mod psi are the same. So they don't change with x. That's what I mean to say here. Okay. So now you can also see that you can have momentum. You can apply the momentum operator on this. And so what are the allowed momenta for the particle? So the allowed momenta are, you apply momentum operator on your wave function on the nth state, let's say, right? And you get minus I h bar d over dx acting on all this stuff, right? E to the power I k n x. And again, just like other cases, it just d by dx is just going to pull out this stuff to the front, and it will leave the function as it is, because it's an exponential anyway. So you get h bar times kn, right, times psi n of x, and because of this, you realize that this is in the form of a number times the wave function, right? And then so that that this is a state of pure, or it's an eigenstate for momentum, right? And its value of the value of the momentum is h bar times kn, and that's h bar times 2 pi by the wavelength. Sorry, 2 pi by L times n, right? So we just found that right there, and then you can also write h bar as h over 2 pi times 2 pi over L times n. And the reason I'm doing that is we get, n times h over L, right? H is the Planck's constant, h bar is 2 pi, Planck's constant by 2 pi. Okay, so now we can also invoke the de Broglie relation and say the momentum of the particle must be h over the wavelength, right? So from here, you can see right away h over the wavelength, and therefore the wavelength must be L over n, right? So wavelength is the length of the circumference of the ring divided by the integer of the state. Right? So n is equal to 0 is the ground state, a zero energy state. We saw it has no wavelength. It's constant all through around. It doesn't wiggle at all. N is equal to 1, n is equal to 2. And as you go up, you can see right away that, as you go up, your wavelength is increasing. It's getting more and more wiggly, right? From here, right? So, yeah. Okay. And again, in classical mechanics, we have this picture that if I have a particle going with a certain velocity here or certain momentum here in the nth state, and it's rotating around a circle of radius r, let's call it big R, right? If it's going around like that, it also has angular momentum, right? Angular momentum, which is this is what you call as the orbital angular momentum, the Earth going around the sun, right? And if it is spinning on its own axis, that is the spin angular momentum. Earth also spins around its axis, right? But this one is the orbital angular momentum. What is the angular momentum? It is defined as the distance times cross product actually, but in this case we can cross product with the momentum, right? R cross P, right? The distance around the axis, and what's the direction of the angular momentum? Let's actually write it in terms of this way. Is that R cross P or P cross R? I think it's R cross P or minus P cross R. So I think the definition of it, you can do your whole physics assuming it's P cross R too. It's not a problem. You just have to take care of that sign. So yeah. But the reason it's done that way, it has an axis, right? And the direction of that is given by the angular, so R cross P. So it will be this way. Okay. And for this case, it's very clear that the angular momentum for your particle on a ring here, if the length is L, so what's the radius? If the length is L, I think I'm going to confuse that. But yeah, let's just write the radius is what? L over 2 pi, right? 2 pi times the radius is the circumference, okay, times Pn is, we just found is 2 pi by L, right, times N times, h bar, right? Correct? So that's our all the allowed momenta as we just found here. Okay, and so now you can see the angular momenta. Sorry, it's unfortunate. Let's write it like that. L is the circumference here, and that's the angular momentum here, the curly L. Okay, so you can see that what you get is the angular momenta for this is integer times Planck's constant, right? So you get that. And so h bar actually is a quantum of angular momentum. That's the physical meaning of Planck's constant. It is a quantum of angular momentum or rotation. Physically, that's what it actually means. And you can take this value, and we know that the angular momentum of Planck's the value of Planck's constant is 6.63 times 10 to the minus 34 joules second, right? Joule second, that's the magnitude of the Planck's constant. And if you take, let's say a classical picture where you have a mass of 1 kilogram, right? And let's say you're spinning this mass on a string of 1 meter length, okay, at a velocity of 1 meters per second, let's say. You can do that, right? Right? Or a basketball, whatever, right? And then you can find the angular momentum for that. For that angular momentum for this heavier object moving this fast, what's the angular momentum? Well, you have radius is 1 meter, right? And mass times velocity is 1 kilogram times 1 meters per second, right? So that's the order of magnitude of a classical angular momentum, right? Of an object like this, right? And so you can see that is 1 joule second, right? So you can compare how small or why is it that it was not discovered till early 1900s, because you couldn't measure this small value. It's 34 orders of magnitude smaller than something that you can actually easily measure in classical physics, right? So but that's the physical meaning of angular momentum, and this is whenever you have spin, or even if you have orbital motion of electrons, it will become important. And spin, the electron spin itself around the axis classically at least an analogy of spin is the electron is spinning around like a top. But remember, we had also talked about it that the electron is actually a point particle. So I don't, it's very hard to kind of have a classical notion of what is spin, because if you have a point particle, what is it spinning, around and all that? It doesn't seem to have a radius. But regardless, it has an intrinsic angular momentum. That's what was experimentally observed. And we will talk about the experiments later. Is this the Stern-Gerlach sort of experiments? But what has been discovered, again, 1920s, 1930s, is the electron spin has angular momentum of how much? What's the spin angular momentum? It can have only 2 values, up or down, and it's half of this, half h bar. So the spin angular momentum, let's write it L sub spin, can be either plus h bar by 2 or minus h bar by 2, and it cannot have any other value for the electron. It's only 2 valued function. And we'll see later the origin of spin is actually relativity. It's a relativistic phenomena. So it was explained by Paul Dirac when he tried to merge relativity and quantum mechanics. What popped out is that this particle must have spin, and it comes out of there. But yeah. So okay. So that's one. That's some order of magnitude of a physical quantity that is very important in classical mechanics. But you can see, the quantum version of it, how small and all that. Again, you can see that this is a sort of a made-up problem, but it's a kind of a nice problem because it really captures all the essence of most things quantum. Yeah. And once you apply a magnetic field, it's a real problem, or if you have a ring, we can today make metal wires or superconducting wires or even semiconductor wires and put them into a ring structure. And when the electrons move around in those rings, you can actually measure these things experimentally. So, So we'll see later it leads to very interesting things like the Aharonov-Bohm effect and all that sort of very interesting phenomena. We're going to talk about those things. Okay. So about this, just to also try to again go back to what I was trying to say. So here's the wave function of any state. And from the wave function, we're able to extract the momentum, its energy, its angular momentum, all that stuff, right? So angular momentum, we did it with an analogy to classical mechanics, but you can apply there's angular momentum operator, you apply it on this and you'll get that sort of thing. So those are, I'm not getting there. But regardless, we can now collect all these states starting from the ground state 0 to the excited states 1, 2, 3, 4, all of them. And now you can see our Hilbert space. What does it look like, right? The Hilbert space is composed of all these wave functions together, each of them. And each one of them is orthogonal to the other, right? They're mutually orthogonal, each one of them, right? And so the notation we want to use for that is if I take state n and m, instead of writing this whole integral and say this is equal to 1 or 0, I just use this Dirac notation, right? N and m. It's a close. It's a vector product, and you can, if you want to have a physical feel for it, you can think this is actually completely analogous to the dot product, But actually, the inner product here is an integral of the two wave functions, cross. So yeah. So in that sense, the vectors are perpendicular. If they're not the same, if they're the same, obviously it's normalized. So that's 1, right? So yeah. Okay. So now let's move on to the particle in a box. Now this is a very important problem, just like the earlier one. I mean, in fact, we are looking at the ones which are going to be we'll call upon them very often. Here we have this extra condition that unlike the particle on a ring problem where there was no potential really, the electron was still looking at a uniform, constant potential. Here there's a abrupt step. So the electron sees an abrupt step, and it's really inside. This example is an infinite potential here, as an example here. So if you have infinite potential, so one of the things is if the potential term becomes infinite in the Schrodinger equation, then I can write again my Schrodinger equation to m d2 over dx squared plus v of x, right, times the wave function is equal to the energy times the wave function, right? So what we're doing is putting the particle inside a infinitely large potential box, right? And so that's our x, it's 0 and L. So again, I think this is a recap, but I hope I'm going to also point out quite a few things that, for example, the BCS, the Bardeen-Cooper-Schreifer theory of superconductivity is intimately related to the particle in the box problem in the end. We'll see that. So there are some things I will point out here which, even though it's a recap, I mean, it's true. So we need to talk about it and also highlight what's important for the particle in the box problem. Okay? For the transport problem. Okay. So here, what are we doing? We are putting the electron in a situation where the potential is infinite on two sides, and you can call it 0 or any value. Let's call it 0 here. So the potential is 0 here. So we put the particle inside this box of length L. And so classically, I think we have already discussed, but again, we can say that if I put the particle there, it's going to sit in the ground state, which is the bottom, right? It will have 0 energy, right? And classically, where am I? If I were to try to measure and find where is the particle now at any point of time, where will it be? Will it be here, there, in the middle? Where will it be classically? So that's an interesting question. So yeah, where will it be if it's sitting at the bottom, right? It can be anywhere, right? There is nothing that tells you it's preferentially here or there or something like that. Right? It can be really anywhere, classically at least, right? And so the probability square of finding this is constant, right? All throughout. Is that correct? I mean, I think that's correct. Right? Classically, there's no reason for it to be found here or there if it's sitting in the ground state. What if it's It's excited state. If you put in the box, but you gave it some energy, right? You kicked it maybe to the right or left or something like that. What if then? Is it still constant probability? The velocity is not going to change really as it goes across back and forth, right? So if you had somehow, I don't know, I mean, just given it some kinetic energy, it will keep bouncing back and forth between the walls, right? But its probability of finding anywhere is not going to change because the velocity is not changing anywhere, right? Right, and the probability of finding at any point in space really is if you imagine I'm sitting here with a detector and every time it goes by, I find over a length of dx here, and I divide it by the velocity. That's how much time it will take to go by, and you can take that time and divide by the period, and you find the probability of finding it there. Something like that, right? So you can do all that stuff, right? But I think if you've done this problem in quantum, all these things change in a big way once you go to the quantum picture now, right? In a big way. It's not. If you are the lower the energy states you are in, the further different it looks from the classical picture. But as you go to higher and higher state, it looks similar. As you go to higher and higher states, it looks similar to classical mechanics. So excited states will look similar to classical mechanics. Ground states will look very different from classical mechanics. So that's the thing. So okay, V is infinite, all right, here. So we want to find the wave function, right? So if V is infinite, if this blows up, you have, what's the choice? What's the wave function here? Right? Or here. Yeah, you're forced to have it to be 0, right? Because if it's any finite number, you can see that this is infinite, so you can have an indeterminate form of it. It's not mathematically, it's not consistent. So everywhere that the potential goes to infinite, the wave function is 0. So the wave function is clamped to 0 here outside. So right? That's done. Now where the potential is 0, which is here, then you already know your solutions, right? This is a simple differential equation. You can, this is 0. Your solutions are A e to the power ikx plus B e to the power minus ikx, right? And this K, if you remember again, is 2 pi. K is related deeply to the energy of the particle, right? Right? And you take this now, and all you need to do is realize that the wave function is clamped to 0 at two edges. And because of that reason, you have two boundary conditions and two unknowns. Just solve it, right? Substitute x is equal to 0 and x is equal to L. Take the psi to be 0 on both sides. You get A and B. Right? Done. So the problem is solved. You find your wave function. And because you found your wave function, you know everything now. Momentum, all that stuff, right? Is that here? So, yeah. And that's the way you solve this. Now, what comes out of this is that K is very similar to the particle on a ring, except it's n times pi over L, not 2 pi over L, but pi over L. And n is 0 is not allowed. N is 0 is not allowed anymore here, right? So the moment you completely quantum confine it with infinite potential, n is 0 is not allowed, because if you do, the wave function becomes 0, and then you actually don't have a particle anymore, because this is what's called the trivial solution, which is not physical. I mean, we're not interested in that solution. But n is 1, 2, and 3, and it can have any sign. And what you get really is, a over b is negative. So a and b have opposite signs. All right. So you get e to the power ikx minus e to the power minus ikx in this situation, the way it's when x is 0 here on the left side, which is why you get, I think that from Euler relation, e to the power ikx minus e to the power minus ikx is a sine kx, 2i times, all that stuff, right? So e to the power I theta minus e to the power minus I theta, right? That's a sine theta, and e to the power I theta plus I e to the minus theta is a cosine theta. Anyway, so here you get a sine x, sine kx, and you can see right away, you can have a I in front and all that, but the complex and so essentially the way it's written here, you can see it's a real number. I mean, it doesn't have a complex version here, right? And right away it's a bound state. The real function is not going to carry any current. We talked about that in last class, and it's an example. But it is composed of two states, e to the power ikx and e to the power minus ikx. And so the particle that's in the ground state here, for example, has momenta at any, if you do any instant, it has momentum to the right and momentum to the left. It's a superposition of the two states. So it's a standing wave. It's a superposition of the two states, and they are equal in amplitude. And that's why the net current is 0. So there is a lot of current flowing. It's just, going equal in both directions. And that's why the net current is 0 for that. And similar for all the higher states as well. Right? Does that make sense? So that's the one way to look at this picture. The second thing I wanted to say was, as you go up in energy, as you increase the energy of the particle, first of all, how does it increase with length? This is again a very important quantity. Energy of the nth state goes as 1 over the mass of the particle and 1 over square of the length of the quantum well, or the quantum confinement. Right? And this is a very important parameter, square of the well width. And we'll see that today, the highest mobilities of electrons in quantum wells, which are used for high-speed transistors and all that, this is a severe restriction. If you want to make a very small transistor, you want to make the length smaller and smaller. But as you make the length smaller and smaller, these energies start floating up, and they, in all physical devices, your barrier height is not infinite, it's finite. It starts floating up, and you have a limitation as to how small can you make one. And not just that, as the length starts varying, sometimes, when you do growth, atomic variations and all that, then the energy becomes hazy. It's not very well defined as you start variations. So this is a very important parameter in pretty much, a lot of these nanoscale devices today, which you are trying to push for highest performance. Yeah. We're going to look at what's called as, quantum well roughness scattering or interface roughness scattering. This is where it comes from. This parameter. Okay. Now. Instead of an infinite well, by the way, yeah, so you can see now that the wave function squared is, this is the wave function. Wave function squared would, look a little not too different from here. For this one, there's a node in the middle, right? So there's no probability of finding the particle here for this excited state. Mod psi squared would be 0 at the middle of the well, as well as at the edges. Right? So you get two lobes here. It's highly probable to find a particle here or there. Right? And as you go higher and higher, you can see there will be multiple nodes, and so this is very far from classical notion of where can you find a particle, right? This is the furthest. But as you go higher and higher, there will always be nodes, and that's classical. That's quantum always. There's a wave function, but then the amplitude of it kind of starts averaging out. And you can see it looks more uniform, more equally probable. To find the particle. So probability would, look something like this, then, 2 humps like that, and so on. Now, this is also a very important parameter, that the fact that, or rather very useful thing, that the fact that you have a node at the center of the well of a particle in a box, because you can use it to design things, and it's actually used to design, for example, if I put a defect here or something like that, at the center of the well, and somehow, I'm not doing transport through my ground state, but for the first excited state, then this state is much more resistant to defects here, if it's in the center, than this state. This state sees all of it, whereas this state sees none, and things like that. You can kind of play these games. So if I put a little barrier or interface barrier, so you can make this one pretty much independent of that barrier, but this one is heavily affected, things like that. So you can kind of do this sort of engineering using these symmetries of the wave functions. So, yeah. What else do I want to say? Oh, yeah. Okay. So this is the infinite well problem, and if you go to finite well width, all real structures will be finite. All right. So for a finite well, as you can imagine, there will be a finite number of states inside the well. Maybe 1 and 2, and maybe let's just look at this state. So let's say this is 0 and state 1. There are two states in this quantum well. Right? And the next state, when I say there are only two states in the quantum well, I mean only two bound states in the quantum well. Outside here, all these energies are still allowed. Right? Does that make sense? And so these are not bound states. These are extended states. Right? These are not bound in the well. So this, and for example, the bound state here will have a wave function. If it's a finite well width, right, a finite well height, it will have a wave function that will it go to 0 at these edges or will it not go to 0? If it's finite, it won't go to 0 anymore. You can go back here. If this is only, say, 3 electron volts, which is a reasonable number for many semiconductor devices, 3 electron volts, 5 electron volts, that's the height of the barrier. Most semiconductor devices or metal semiconductor junctions or quantum wells. So if you put that in, you can actually, you see right away that the wave function really doesn't need to vanish anymore. You can solve this. It's just like a, light. If you try to fit light into a waveguide, and the wavelength of light is bigger than the waveguide, so it's just the same problem really. The electron wave is fitted into this well, but it can have its wavelength will typically be a little larger, so the wave function will, the ground state wave function will look something like this, and then it will decay into these wells. There will be evanescent tail, right? Evanescent tail. And you can see that from just again this idea that the energy of the particle is h square k square by twice mass of the particle plus the total energy. Again, this is plus the potential energy, all right? So if my energy is here, if my total energy is here, right? This is so. All right, this is my energy axis. Then, if the particle physically is between 0 and L here, right? Then its potential energy is this value, right? Let's put a 0 somewhere. All right, let's call this as our 0, right? So potential energy is 0, and the kinetic energy is all right. So if the particle is here, the kinetic energy, the potential is 0, so the kinetic energy is something positive. So it has some wavelength associated with it, right? Does that make sense? So this is 0, and this is some kinetic energy total. You can find out right away. You can find out what's the wavelength, right? What will be the wavelength? Will it be? So if you had a infinite wall, the wavelength will be exactly twice the length of the well. You can see that, right? The infinite wall, the wavelength is twice. What about here? Will it be larger, smaller? What will it be? It will be larger. You can see that right away, right? Because it leaks out a little bit on both sides, right? So it must be a little bit larger, and you can calculate exactly how much it will be by doing this thing here, right? The wavelength is larger also means that its energy will be what, larger or lower than this one, the ground state? It will be lower. Whenever you let a particle sample more space in real space, its energy is lower. This is called delocalization. And this is an example. If you let the wavelength go across, further stretch out a little bit because you have finite barriers instead of infinite, the energy will be lower compared to this. You can calculate all these things exactly for the particle in a box problem, right? And outside here, the wave function is decaying, right? Is decaying exponentially, right? It's an exponential decay. And how do you find that? Rather, maybe you can help me with this. I mean, how would I write down the wave function here? See, the thing is, wave function, you can always write it as a e to the power ikx plus, or rather, if you want to find the k, you can always write this relation, and it will give you an idea of what the k is, right away. Now, if I am here, if my x is at this point of location, x-axis, then what is my v? It's like 3 eV, right? 3 eV. But I'm looking at this ground state. I'm not looking at extended state out here, right? So its energy is what? It's maybe, let's call it 0.5 eV here for argument's sake, right? So the total energy is 0.5 eV, right? So you see right away that this quantity must be what? Positive or negative? So if that's 3 electron volts, that's 0.5, and you're adding these two quantities to get 0.5, this must be negative, right? So the kinetic energy is negative, right? That's our classical notion of kinetic energy. Kinetic energy is momentum squared by twice mass, but it's negative, right? And that, is not quite allowed in classical mechanics, right? Kinetic energy is not negative. Half mv squared is not negative, right? But here in quantum mechanics, it is allowed because of its wave nature. And kinetic energy can be negative if k, I think we know that h bar is not negative, right? And we have a square of it. So h bar is not imaginary, so that can't give you that minus sign. Mass is not negative here, right? So the only option left is k, and k squared is negative, so k becomes imaginary. So it's an evanescent state. K becomes imaginary. So you can write k as an imaginary I times a kappa. That's what is typically done. You can write it in that way. And then solve this. And from here, right away, you can find out what's the order of magnitude of kappa, because what you get is h squared kappa squared by twice mass, but a negative sign, plus v is equal to the total energy, right? And you can reverse all that stuff and write that k squared is 2m over h bar squared times v minus e total. Kappa squared. Okay. So anyway, kappa, or let me write it in this way. Small k is I times square root of this whole thing. So that's right. Okay. And you can still write this as 2 pi over a certain wavelength. You can still write it like that. It's okay. I mean, obviously the wavelength also becomes imaginary if you might want to think of it. This is nothing but an evanescent wave, just like light when it's incident on an air-glass interface, right? It actually, a little part of the energy goes into this, into the barrier. And this is what is physically called tunneling. It is exactly what electron goes in, hits there, but then a part of it tunnels through a little bit, and then it decays back and it returns. It's kind of so the return or the reflection is not quite at one point in space. It tunnels in and then returns, tunnels in and returns. Right? Does it make sense? So that's what's happening here. And you can quickly estimate how far is it tunneling for any electronic device. Typically, if you plug in these numbers, you can use an effective mass if you might. This is about a couple of electron volts, Planck's constant, and you can find a characteristic length it will tunnel, right? And that will be a few angstroms, typically, few angstroms. Maybe, typically less than about a nanometer. So that will be like 4 or 5 atomic constants in a solid. That's how far it's going to, have an impact, and it will kind of, tunnel through and then come back. So, yeah.
So you're saying when the wave propagates by some period, that's what you call that?
Yeah. Okay. Yeah. Right. So every time I have a finite barrier height, the electron, I'm in a bound state, it will tunnel through a little bit and come back here, right? And it will reflect, but and it's a bound state, so it's going to continue doing that, right? Now you can take advantage of this fact. So again, just to be clear, summarize this. We have I think a good order of magnitude to remember is if I have 1 eV barrier heights, and I think for effective masses of 0.1, the tunneling depth is about 1 nanometer. And that's a rough order of magnitude. And so in semiconductor devices, this is actually very, very important now, because as you make a transistor small, in a silicon transistor, the electrons that are doing all the current flow are actually sitting in a quantum well like this. Okay? And what you have here, the barrier, is a silicon dioxide or a hafnium dioxide as a high K dielectric or something. It's a dielectric insulator, and then there's a metal on this side. Right? And because the transistors have become very small, this thickness has been shrunk, and now it's down to a couple of nanometers. Right? And then you can see that you have a problem because the insulator is not going to be able to hold back the electrons. It will tunnel into the metal. So that's called gate tunneling. And this was a big problem, and in mid 2000s, about 10 years ago, people introduced high Ks and metal gates to fight this problem in silicon transistors. So this was a big change that happened because we want to avoid this problem. Right? you can take advantage of this if you want. For example, if you have 2 barriers instead of 1, you know. So or in other words, I can put in another well here, very close to it. Wrong color. Hold on. Another barrier, another well here, very close to it, and I can make these states resonant, and I can actually have the electron, you know, actually we can create a situation when it tunnels in with a probability of 1. That's called resonant tunneling. You know? So you can get out. So you can. So that thing is very analogous to this picture of you know. Here's the analogy, classical analogy with light. I think I kind of, you know, like this picture a lot because you can take a prism. I'm sketching it the wrong way. Okay, so I can take a prism of glass and I have light incident here, and we know it reflects, right? Right. But then, if you look closely in electromagnetics, there's a little bit of light that leaks out here. That's the evanescent part. But all of it gets, you know, again reflected back, just like the electron gets reflected back with a barrier. So, but you know that if I take another prism and I, you know, stick it here, you know that the light is going to come out because it's a square. I mean, it's a cube now, right? It'll come out. Why does it come out? Physically, it does come out, and that's because you're pulling out the evanescent state, or the, you know, the light photon is able to tunnel through. That's the classical picture. This is, you know, exactly the same thing you're doing, either in a resonant tunneling structure or sometimes in a PN diode. You know, it's a Isaki diode. These things are where you use the evanescent state or the tunneling state of the electron. Okay, so that's one point. Another interesting point is whenever I have a two-state system like this, 0 and 1, you know, I can create superpositions in it with certain coefficients, and these are today, you know, classical computation is done with classical bits of zeros and ones. But if you take this sort of a two-state system, you can create quantum states, and these are called quantum bits or qubits in quantum computation. So, you know, essentially they are also, you know, particle in a box problem in the end. And it could be atoms, it could be quantum dots, it could be all kinds of things. But, you know, these two-level systems are what's used for qubits or quantum computation for the future. At least, you know, people are trying to make qubits for computation in the future. Yeah. Okay, one more thing. So if I have a finite well, finite depth well, let's try to sketch if I have an electron that's incident from this side, from outside the well. It's coming in from here. Maybe you can help me to sketch for this one well, how will the wavelength look? And if the electron has this energy here, and that's the energy of the electron. Its energy is actually larger than the barrier here. And it's incident. It's coming along like that. So it has a certain wavelength here, right? So what is the wavelength? Let's call this as, so what would we call this as 0, and this is, let's call this as V0, the height of the barrier. And let's call this as, you know, some E0 is the kinetic energy, right? So maybe you can tell me, these are things you should be able to kind of write down without, you know, or rather have some intuition for it. So what's the wavelength? What's the K of the electron here? How do I find that? How do I find the K there? Yeah, yeah.
It's like h bar of the square root of 2m.
Yeah, so you can just write a square k square by 2m is the kinetic energy, right? And that's just E0, right? Then and so therefore K is 2m E0 over h bar squared, and that's 2 pi by the wavelength, so you can find, right? So right, so that's, yeah, I wrote that here, but you know, if you have the total energy, you can do minus V0. All you need is this kinetic part of it, right? So it has a certain wavelength, right? And we just found what it is, right? Now it's going to be incident on this well. So here you can see, so just like light being incident with a difference of refractive index, it's the same problem. There'll be some reflection, there'll be some transmission, right? That's what's going to happen. And so there'll be some reflection, some transmission, but regardless of that, I want to ask the question, what is the wavelength here? Maybe you can tell me that. What's the wavelength when the particle physically is somewhere, you know, around here within the L, 0 to L?
Larger, K is larger, so light wavelength is smaller.
It'll shrink, right? The wavelength has to get shorter. Why? Because suddenly it finds its kinetic energy is very large, right? Because the potential energy just dropped, right? So the kinetic energy is very large, so the wavelength must shrink. The k has to go up, and what is it? It's basically in region 2, it's E naught plus this V naught, right? So that's how it will become more wiggly, and then when you actually do all the matching of the waves and all, it will become a little more wiggly like that here. And then when it gets out here, I think you can see if the barriers are the same height on both sides, it will go back to the same wavelength again, right? So this is a picture of that, right? So adding up all the reflections and transmissions. So one of the problems you're solving is very similar to this, really, in the assignment, right? Very similar. So you can have an incident wave with an amplitude of, say, 1, and a reflected wave here with, let's call it A amplitude, transmitted wave, wave going to the right with B, wave going to the left with C, and finally a wave going to the right with D. So there are 4 amplitudes, right? And each of these wave functions, for the right going wave, you can see that this, if I am just writing the wave function here for the right going wave, it's exactly the same as your free particle wave function. There's no difference, right? It's this problem, right? In separate parts of the, and therefore, what is the total wave function here, right? I write 1 is the amplitude times e to the power I kx. That's the right going wave, right? And k, I can find out, we just wrote it, k is given by the kinetic energy. So that's k1, let's call it k1, right? Plus, what did I write? A is the reflection coefficient, amplitude of the reflection, times e to the power what? Minus, right? Because the reflected wave will have the same k, but minus sign. It's going in the other way, right? So it's just a momentum from intuition. You can write that, k1x. So that's your wave function of the particle anywhere, less than 0.
The first term is the incident?
Yes, that's right. So we are just saying you can assume the incidence to be, you can assume it to be another variable, but you can assume that the problem is set up such that we say that a particle is incident from the left, right? So we actually launched it from here, in which case it's 1. We know we have set it off here, right? Okay, so similarly, what do you write here in the middle? So you can see B, right? E to the power I k2. That's k2 here, right? Its k is different now, right? k2x plus c e to the power minus I k2x. Right? And finally, here we are saying, if it was incident from on the left side, it was not incident from the right side. So the only thing is it's going to the right, right? So I have only d e to the power I k. If the barrier heights are the same, you can come back to k1 again. Right? The k's here and here would be the same. So we can come back. So what I was trying to get to is now you have the wave function at all points in space by just using this picture, and all you need to do is and we have said that if I know the wave function, I can solve the whole problem, right? I can find out everything about it. And there are 4 unknowns, right? There's A, B, C, and D. There are 4 unknowns. And how do you find those 4 unknowns? You use boundary conditions. You match the waves, right? You match the wave function. So the wave function must be continuous across this interface, and its derivative must also be continuous. Now the derivative has to be continuous because of current, and we're going to see that later. We remember in the current there's a derivative in space, right? Gradient. So that's to conserve particle number, right? So the current is continuous and the derivatives are continuous. So you get 2 equations here, 2 equations there. You got your 4 equations, right? So you solve the 4, and you get ABCD, right? Done, right? And you can use Mathematica, for this sort of thing. It's very nice to use for analytical expressions. You can just set it up and say solve it, and it'll solve the whole thing and give you all the answers, analytically. Or you can do it by hand. I mean, I'm not discouraging that, but I'm saying that you can even, if I have a resonant tunneling diode where you have multiple interfaces, then it gets a little out of hand, if you so to say, right? So, but you can set it up, and you can see that if I build up a solid where I have an atom here, all these wells, you can build up a whole periodic crystal like that, right? And then what it'll give you is band structure. We're going to talk about that a little later. Okay. So in this problem, then, if the particle was incident from here, and let's say I found out all my coefficients A, B, C, D based on based on all these k's and these potential barrier heights and the length of the well. What is you can maybe I'll ask you the question now, given what our discussion in the last class. What is the net current J, or the flux of the electron wave going to the right here on this side? What is it? So J on the right side, in region 3, if you might, on the right side. What is? How do I write that? Yeah.
The wave function conjugate times.
Yeah. So you can always use that trick, right? So you can write down its psi star gradient psi minus psi gradient psi star, right? Over 2m. Momentum operator and momentum operator, right? So you can use that, and you can obviously plug that in and see, right? But I want to say, for this problem, yeah, this is your brute force, but you can use your intuition and say, what is it, right? So physically, what is going on? See, here you have a wave that's going to the right. It's a free particle, right? And the velocity of that particle is h bar times k over mass. It's a free particle, right? Right? And its amplitude square, if you look at the wave function, is just d, right? So the net current, if you evaluate it there, will be mod d squared times h bar k over mass. That's what's going to be a current in that point, right? Does it make sense? And you can evaluate it. You can, just like you said, you can plug it in, and it's good to check, and you'll see you should get this in the end, right? So this is the net current. What about the current coming in from the left? What will that be? Or rather, sorry, let me say, what is the net current here? So the quantum current flowing on the left side. So it's a great, I think it's the fifth class, so I'm very happy we're talking quantum transport. This is proper quantum transport, we're going to look at it in many cases, but this is, yeah.
It would be h bar k over m because we set the incident amplitude.
Yeah, so I should have written like K1. Yeah, h bar K1 over m. Because we have said that the barrier heights are the same, so this K here times. But then, is that all? Or not? Because remember, we have set it up that there's incident is 1, but there's also a reflected part, and that's A. Right? Amplitude of reflection is A. So what should I get here? If you use your classical quantity, mod square of the coefficient is proportional to the probability, right? So when you evaluate it, you will get 1 minus mod A square. You should get that when you plug that in there, right? And I'm saying, you can just say the wave function here is just that, and you plug that into your quantum expression. You should get. Right? Yeah. Remember, A, B, C, D are all complex numbers, so you must be careful with that. If you take it to be real, you will not get these things. Okay. And finally, by going by the same token, what should it be here inside the well region? So you can see it will be b squared minus c squared, right? If b is the right going, c is the left going, times h bar times k2 over mass, right? Inside the well, between x is L and 0. This is for x greater than L. And this is x less than 0. And each of them, all of them are equal to each other. This is current continuity. Current must be continuous. So that really tells you that 1 minus a square must be equal to b square minus c square, which must be equal to d square as well. Right? Yeah.
And over here, you're only including one reflection, right? But c also can get reflected and transmitted, and that can occur like infinite times too.
Very good point. Yeah. So what we are solving is, when you solve it this way, when you match the boundary conditions, all that is taken into account. So all the multiple reflections, Fabry-Perot's are taken into account. It's a very good point, right? So you're saying that classically, I can imagine the particle going here, part of it is reflected, part of it is transmitted, part of it is reflected, part is transmitted, and the part of it is reflected goes back and forth, right? So you get a cavity. If you solve the problem using, the boundaries, so that is already solved for. But it's a good, it's good to remember that all this stuff is going on physically. Yeah. So yeah. Okay. So now, using this sort of picture, you can actually build up and solve the more complicated problems than this. But I think it's a good point to make. And the last thing, we can have a break now. But the last thing I want to say before the break is another very important result of a particle in a box. All this is 1D problem. If I have a 1D problem like this, and you can imagine this electron, we said, is coming in with this energy, right? So out here, you have kind of a continuum of energies. And physically, if we do not allow it to scatter, if we don't allow phonon scattering and all that, this is what will happen. We talked about just now, right? That's exactly what it is. But if you are in a crystal, and this is kind of a quantum well, and you're shooting an electron over a well like that, there is a chance, it has a finite probability for that, there's a finite probability for the electron to, emit a certain number of phonons and get stuck here. So it will emit maybe 2 or 3 phonons or 2 or 3 photons, depends, depending on energies. And it will get stuck here. So this is a bound state. It will capture, it will trap that electron. And this, we can calculate later how this process might happen, what are the time scales and all that. But there's a finite probability it can get trapped. Right? But I think you can see that if I have a lot of electrons incident on this side, this well can only hold a finite number, right? If in fact, it can hold 2 in the ground state and 2 in the upper state, and that's it. 4 electrons, with up and down spin, because of Pauli exclusion. So that's something that happens in many semiconductor devices. Charge gets trapped, and when you get trapped, what happens is this potential barrier. This is a slight more complication. The potential barrier height doesn't look like this. It starts looking more like this because the electron is repelling the other electrons now. So it starts floating up and down now. And that leads to things like Coulomb blockade and all that sort of thing. That's called Coulomb blockade. You can see what it is. It's just Coulomb repulsion that's making the harder for electrons to get into the well again. So that's Coulomb blockade effect. Right? This happens very often in what's called single electron transistors. So this is something that people deal with. Okay. Now, as I start shrinking the height of the well, I can make it very, very shallow. Will I, you can see that intuitively it will be difficult to have a bound state inside. If I make it very small, first of all you have 2 and then it'll become only 1, right? And if I make it smaller and smaller barrier height, will I still have a bound state or not? Right? So this is a very interesting question, by the way, right? So in one dimension, if you have electron transport 1D, you will always have a bound state. That is guaranteed, at least 1. So 1 is the minimum, and you can prove it by matching boundary conditions and finding out, what is the energy. You will see it's always 1 bound state in 1 dimension. Yeah. Right. Yeah, good point. So let me just say, for symmetric wells only. If you make it asymmetric, you can actually push it out again, right? But symmetric wells, good point. Yeah. This is a famous Landau-Lifshitz problem, so you can look at it. But yeah, if you have a symmetric well, you are always guaranteed to have 1 bound state. And this will have very important consequences for superconductivity later. This is the reason Cooper pairs form, because you are guaranteed there is a minimum energy for this sort of thing to happen. If you go to 2 dimensions, again, you are guaranteed to have 1 state, but that state will be what you call as exponentially small. The trapping or the confinement will be very, very weak. It will be exponentially weak. So at room temperature and all, you cannot see it at all, but at very, very low temperatures, you can actually see that. And in 3 dimensions, you can push the state out. You can have 0 states inside, 0 bound states in 3 dimensions. So that's a kind of an interesting result, which will have some consequences later. And you can see this is a model for traps, for all kinds of things, resonant tunneling. In fact, I'd go so far to say that pretty much all transport phenomena is related to the particle in a box problem. In fact, pretty much all of quantum mechanics is related to the particle in a box problem. And so that's why it's kind of an important problem. Okay, good. So we can take a short break, maybe 5 minutes. And the next I wanted to talk about a little bit is the harmonic oscillator before we go on to the transport, back to some transport stuff and look at, today I wanted to look at a little bit of the ballistic transport through one quantum wire. We are ready to do that actually now. We can show why conductance should be quantized and that sort of thing. We are ready to kind of look into that. But I wanted to, let's take a 5-minute break and then we talk a little bit about the harmonic oscillator, specifically for no other reason than to develop this formalism of what's called the raising and lowering or creation and annihilation operators, because we want to use it in later parts of the course. This is just to kind of discuss that a little bit today. So, okay, good. So let's take a 5-minute break. Yeah.
Yeah, so here it is easier. Here it is easier plus this. And then here it's again easier. That's right, you were right, it's only the difference. Yeah, it's the kinetic effect.
Oh, is it the jump guy? Is it the guy who has like a jump?
It will be, yes.
No.
Okay.
No, it's very.
Okay, so the wavelength there is not well defined. But I'm saying this is a measure of the decay length. It's not really a wavelength anymore. It's 2 pi by some characteristic decay length. Yeah, that's right. So that's what it is really not going to oscillate.
Nanomaterials. That's with
Right, so what you're saying is, yeah, so if I, remember for any wave, you can have partly going to the right, partly to the left. So here the right going amplitude is 1 because we launched it this way. No, yeah, that's a good point. So there's no barrier
Analog device.
physically, but you can see that there's a wavelength mismatch. Meaning, here, right. So here you have a long wavelength, and here you suddenly have a small wavelength. And so as a result, you will always have some, you will have some reflection unless you do something to prevent it.
That's also like but I'm probably gonna audit.
Oh no, all this was developed to explain experimental data.
Like because
No, absolutely. So this is a measure of reflection.
barrier actually had every
And this is
single day.
completely analogous to light.
Exactly.
Light,
And, if
it's
I had to do
incident
this one, I would have died. Like because I was supposed to do a solid state
because the wavelength gets
today.
shorter inside.
Weak for that class. So that's why I'm going to just audit that class. The reason is because I'm going to apply
Going to the right.
for my PhD like
The network.
semester. So I was talking. So I was talking to Tiwari. He knows everything that what I want to do and stuff. So I want to try to do more of quantum computing stuff. So he told me that I'm going to apply to at least have some sort of like solid state and explain my coursework to show that I actually know these stuff. And I've read all these on my own, but I actually can't show to people that I actually
Right.
know.
So if you place it in, say, state 10, and it's 1 for 10, if you place it there and the particle is in that box and there's really no other thing to happen, it will stay in that state. But physically, if you think of it as a point particle, it is always rattling back and forth between the two walls.
Like the anomaly of I think like last.
Yes. So meaning if I were to measure it between x half L by 2 and L by 2 plus stuff delta, I can find there's a finite probability associated with it because plot the probabilities mod psi square, it has all these nodes as maximum because it goes to 0.
No, I made this.
The wave function is oscillating. So there are some points, if n is equal to 10 state, there are 10 points along that line where you would never find. It's a standing wave.
Yeah.
No, the energy of that
How
particle
much
is
quantum do
constant.
you think I should know?
The energy is constant. But its state is just that the probability of finding it is
I was
changing.
talking about like
Its energy is
this is
constant.
actually a really smart guy. Like did you take one of his classes?
I took the
Yeah.
Then it's a
Might be-
superposition of states.
I would say his teaching is a little
It's meaning if the initial energy is between 5 and 6,
class might be almost no equations.
then it's a superposition. It will go back and forth.
I
between
took
two.
I don't know how he thought.
So, and that thing will evolve with time.
Introduction to silicon voice fundamental. Yeah, so it was mostly just like, which is good, like because you get all the electricity, but then you also want to have
in solving the
if
problem
someone asks you what you know about the device, I'll be like,
so I set it up. I'm pretty sure I saw that. As you went down more than I ended up with
So like, what I took away from the semiconductor physics is like, I am aware that certain concepts exist,
four equations
but
where
I have no idea.
linear and
exactly, in terms of like the equation.
variables and
But then like, if you read his books,
I tried to
he
solve
actually, at least somewhat explains the
even
problem.
that it was
Oh, if you have tried solving
And
these
yeah,
mathematics, if you have
at least when I was
issues, you
talking
can
to him
share
like
it with me. I
separately, I
can
felt like he actually
let
let
you know if there are any.
well, we were working on it together, so
Okay.
I'll come to you after
Yeah,
class.
yeah, and, or, yeah, okay, right
He
after.
actually, like I talked to him, I just want to do one thing.
Are you talking about the first problem?
Really,
No,
The
four.
Really? I couldn't solve the first one.
like the math.
Oh, the first one is.
Which of all the
Oh, you're not supposed to.
because in the undergrad, all it is.
The first problem.
I mean, many math classes
Pretty
are
straightforward.
Right, so if you have a free electron minus its energy and it has no other way to lose its energy,
There's
meaning,
no
you know,
differential.
if you put it inside a crystal,
Can I see that?
Seriously?
you know, but he told me like no matter what, you don't have to join your sport, you need a
so what you can do, here's an example, physical example of a free electron. We have vacuum, we have a lot of enough liters, you can have a wire and then have what's called a field efficiency, you have a tip very sharp, and you apply large voltage and the electron will escape, which will actually go into the vacuum. And then in the vacuum, you use a free electron because it will keep going forever till it hits something.
Yeah.
This is a physically how you create. In fact, in these are very long tube lines.
I feel like that's what I thought that all
No, there are gases, it will collide once in a while, molecules, but mostly it goes like this. And then every time it hits another gas, it will light up, that's what the light creates.
go to the physics department, like
So it goes like a field electron for a certain distance.
So as a
over here, like it's all like party department, they're gonna like only things about it is situations that they're not even might be. And then if you go to the math department, it's even more. And I feel like you take some class in math department, you take class if you want to
Say that again? What?
and then
But the weird thing that I discovered is like,
They must equal each other and the derivative must also be there.
is a requirement for physics, but not easy. Like the applied physics does not take the applied quantum.
No, that's true.
Regular physics.
Yeah, the wave function must be the same, from both sides, and the derivative must
It's how it changes. Or because they have these requirements, like half a semester type class, like half a semester for intro to quantum.
No, that's right. So the reason for that, as I was mentioned very briefly, is the reason for that is because that conserves
I
current.
know right now it's like one semester.
Current, because current has a derivative, current as d by dx of the wave function. So to conserve that, conserve current, it must actually also. Yeah.
I still don't know.
I mean, no, not necessarily. You can have a quarter or a half wavelength inside, but just that the wave function slope must not change. It must be conserved.
When it comes to interactions with light, you don't actually know how to use the equations over there. I know how to use like other equations, but not the equations. You get what I'm saying?
Well, I mean, there's like,
I don't have it all worked out.
No, that's the thing. And I was
So
researching
solvent
like,
solvent is the first.
I think you have to know how to use
Okay.
if you want to, like, you can think of like the field light itself as phonon and photon. So you think of it as a particle, and you think of this as a particle, and you think of the particle-particle interaction. So I think I would think of field interaction. So I was like, oh crap, I'm gonna try to take the field theory class this semester so that I at least know all these stuff. And I did. I went for like 1 week for that, but then I realized that I'm gonna apply my patient, like if I show them that I have like a fever, if I have a fever, actually like, it's more like, and I, you know, the class they were more oriented towards like quite you know, yeah. Much fun. But yeah, the project is very cool though. At least now I understand what
I mean, just reading the description about it,
yeah, I was like, oh, what do I have to do? And like, knowing Giovanni and part-time master nothing. He was just talking in like terms that I had no clue. And then he took me to read a book, one of the books that you were talking about. Yeah, so doing all these stuff, I feel like it's probably like I spent like half an hour, and right now I feel like I thought they gave stuff to do.
No.
Okay, no, then like he gave the paper like Friday. I mean, he gave the paper like 2 days back on Wednesday. And he told me to come back reading all the 5 minutes after the day. Yeah, so what we're doing is, I'm doing some problem generation.
Oh, we. So. Okay, so let's continue this discussion. I think there were a couple of questions that were asked. For example, if I have state, 1, 2, 3, and let's say somehow I try to push an electron into this well which has an energy between 1 and 2, right? It's not 1 or 2, somewhere between 1 and 2. So what will happen then, right? Good point. So it can, if it was in a solid, or it can emit a phonon and get down there. But let's say we are not we don't allow that. We forbid photon emission or phonon emission for it to go down. Then what will happen? First of all, it's actually difficult to put an electron in because it's not an allowed state. But let's say somehow you manage to get it in. Yeah.
Form like a superposition.
Yeah, it will form a superposition of the two states of 1 and 2. In fact, it will have some amplitude for many other states. So how would you physically realize this? Actually, it's something that happens in devices as well. So I can have a well width like this, and let's say the electron is sitting in the ground state. Okay? And then by some means I make the well width like twice of it at t is equal to 0. And you can do that with the electric potential externally and stretch the well out. In which case you can see right away the ground state will float down, and suddenly you have created that situation where an electron is neither in ground or upper state, but it started out at that energy which is intermediate, in which case it will become a superposition now. And that is how most of the qubits are done today, where you start out something and then you select which state, 0 or 1 it is, and all that. So, yeah. Okay, so we want to talk a little bit about the harmonic oscillator, which this is also a particle in a box, as you might imagine, but the shape of the box is a parabola, right? So the potential V of x is, instead of being 0 and some value, it's a parabola, and what it does is unlike the particle in a box where your energy is changing as n squared. Go from state 1 to state 2. State 2 square is 4. State 1 square is 1. So you're increasing as the square, right, of the quantum number. The energy is becoming farther and farther apart as you go out, right? And if you have a finite well, there's a certain number of bound states, and yeah. But now if you kind of shape it out like that, then the harmonic oscillator is another extreme of that, where the energies become uniform, right? So the energies become uniform here, and the energy separation, again found initially obviously by experiments and all that, is given by this. So let's kind of write down a few things about it, because this is going to be an important part of this course later on, at least the techniques we are going to use here. So potential is a function of x, and it's something like this, v of x, right, is half. Typically what you look at it as is a mass spring system. You have a mass that's small m, which is an electron, let's say, and then there's a spring with a spring constant of k. It's not the wave vector, spring constant, and then if you stretch it out, it will oscillate, right? So that's a harmonic oscillator, and it manifests in many ways, as you might imagine. If you take in electrical circuits, you take a capacitor and an inductor. That's your LC harmonic oscillator, for example, right? I mean, all kinds of things, right? So we don't want to get into all that. So so instead of half kx squared, so we also know that the frequency of oscillation for such a mass spring system is given by square root of k over the mass. Oh yeah, I think the most important one I forgot to say is the pendulum, right? So okay. Mass, sorry, it's a harmonic oscillator. So it oscillates around a point, right? All of them have the similar, physics. So omega is the frequency is given by square root of the spring constant k, big K, yeah, over the mass. Okay. And from here we see that the spring constant in general is mass times square of the characteristic frequency, right? And typically we write it as half big K x squared is the potential term of the spring, and so instead of writing it like that, we will write it as mass omega squared times x squared. Right? So if we're talking about an electron in a harmonic oscillator, this is the mass of the electron, and the shape of this well or the potential is completely determined by this omega. Right? That's what determines it, the shape. If omega is very large, how will the shape look? Omega is very large. It'll look, like that, right? And if omega is very small, it will be something like that. Right? So that's the physical meaning of this frequency. You can translate it to a stiffer spring or a weaker spring and all that sort of thing. Right? So, right. Okay. So now the problem classically is very easy to solve, right? You can solve ball rolling back and forth if you start out at a certain energy. And when you do the quantum version, you solve Schrodinger equation with this v of x, right? H squared by 2m d2 by dx squared plus, half m omega squared x squared of wave function is equal to E psi, right? So you can solve this equation, and this equation leads to these eigenvalues. And I think you are doing this in your assignment problem anyway. So certain wave functions where you have some quantity out in the front, which is a Hankel function, the Hermite polynomials and all that sort of thing, and then you have a half m omega squared x squared over h bar omega. That's a characteristic wave function, which for the ground state is a Gaussian, right? Instead of a sine function or cosine function or a plane wave, it's a Gaussian function. So e to the power minus x squared. So that's how it looks like. And the characteristic energy is h bar omega for this. Right? And there's a mass and all that. And there's this other factor here. That other factor, as you go up to higher states, starts oscillating faster. And so it'll look something like that. And then 2 nodes and so on, right? As you go up. There'll be a 0 in so this is called n is equal to 0, n is equal to 1, 2, and so on. Right? So the number here counts how many zeros there are, how many nodes there are. Right? So it's the same thing, right? Right. So that's okay. And the energies that you get out of solving this is again nth energy, nth eigenvalue corresponding to this wave function is h bar omega times that n plus half. That's what you would get. This is the complete solution of the harmonic oscillator from the time-independent Schrodinger equation. Right? And you can make all kinds of physical connections to what this means. So clearly this means that the probability mod psi squared is highest for finding the particle at the center, and it decays. There's always a finite penetration onto both sides. that means the electron is again tunneling a little bit into the barrier and tunneling back again. So that's all the same, very similar to particle in the box, the square potential, right? Okay, so, and then here's the full-blown expression for the nth wave function. So you have the whole thing written here. You have a normalization factor, you have all this stuff out here. Okay, any questions on this? I think this is hopefully okay. Now, the reason I'm really talking about it is to, something you may have done in your earlier courses, but I wanted to kind of cover that in some detail in this course and set up for what's coming later. So I want to write this Schrodinger equation in a slightly different way and see where it's going to lead us. And this came out of basically some analysis that Dirac was doing. Just essentially was basically playing around with the mathematics. He had no real intention of doing anything deeper than just looking at it in a slightly different way. Okay, so Dirac is very famous, and we'll see later, for taking square roots of things. He's been taking he took square roots of many things. So he was okay. Let's see why I'm going to say that now. And the square root business is going to lead to all this topological stuff later. So I'm bringing it up right now. And it started with this picture. So he said, well, let's look at this. This is x and p. We know that x and p are have this relation that if I take x comma p, which is the commutator xp minus px, right? That's equal to what? It's actually a number, right? And what is that? It's the answer. Yeah, it's I times h bar, right? This is very precise. It's exact. So this is what the quantum mech is actually. It rests on this relation. All of it rests on this. So he said that clearly the masses and the frequencies are things we can factor in and all that. But he says that this is of the form. If I look at the x and the p, it's of the form a squared plus b squared. You can see that. I mean, all these other constants are fine, but operator-wise, it's in the form operator x squared plus operator p squared. Right? So, in fact, let's write that out. Also, by that time, in fact, even before that, people had already found the eigenvalues from a differential equation perspective. They had found that these are the eigenvalues, right? And I think you can say without much, even before going there, that h bar omega must be the characteristic energy of this thing, in quantum mechanics, because omega is the characteristic frequency, h bar. So let's pull out a h bar omega from here and write this as m omega squared by twice. Right, so, yeah. Okay, so could we put it on this side? Right,
There's 2 liters. I would like to come back.
Okay, no problem. Thank you. So, all right, so we kind of pull that out and just normalize this like this. P squared over 2m h bar omega, right? Psi is equal to same thing. Right. And you can see right now that all this stuff inside is now dimensionless, right? It has no units anymore. But these are operators. Just remember that. These are still operators. And so now we can write this quantity. We're going to just define this quantity as, let's say, operator A, all right, squared, and this quantity as operator B squared. Right?
Is that
Yeah.
x hat?
Yeah. Oh, sorry, x hat squared. Yeah. Squared. X hat. Oh, yeah, half m omega squared. So it's the x squared potential, and we are looking at it from an operator perspective. So in this picture now, right? So these are not numbers. X and p are not numbers anymore. These are the operators, right? Or these are matrices, if you want to think of it that way. That's what it is. Yeah. So now we write it as a squared plus b squared, and I think you can probably tell me what is the well, before we go there, let's see what is a. Let's note that down. That's m omega. So there's one omega that cancels out over 2h bar square root times x hat, right? From here, and this b hat is square root of 1 over 2m h bar omega times p x hat, right? All right, so maybe you can tell me what is how would I find something like a commutator with B, right? You see, I don't really have to do much, right? Because I already know X and P commutator, right? X and Px commutator. All the stuff sitting in front are constants. They can just pull it out of the commutator. It doesn't matter at all. And when you multiply these two quantities, what you end up is h bar, 1 over 2 h bar, right? It's just the constants here. And then you have commutator of x comma px, right? And what is that? That's this I h bar, right? So all we have, we just basically multiplied constants to this quantity. So I h bar. And so A commutator B is actually just I over 2, half I. That's what it means. Right? So yeah. Okay, so that's all interesting, but actually pretty much useless because we have just redefined quantities. That's fine. And now he said that let's see, let's take a square root of this thing now, right? So a squared plus b squared. What is the square root of a squared plus b squared? Yeah. So this is a squared. Let's write it as big A because we're right. All right. So now you got to think a little bit outside of real numbers. So a squared plus b squared. What's the square root? Yeah. Sorry. Yeah. Yeah, that's right. A plus I times b, right? So you can have a plus ib and a minus ib, right? Right? You can do that. But actually, this is true only if a and b are numbers, complex numbers, real numbers, whatever. If they're operators, this is not complete, right? So if they're operators, multiply this out. If they're operators, I put a hat, right? Which actually they are. A and b are operators here. If I put a hat, what do you get here? You get a squared, right? And you get plus I minus I will give you b squared for sure, right? That's fine, this and this. But then you get what? I times, you can see here, b a minus a b, right? So a little careful, right? So if they're operators, this is what you get. And that's, you identify that right away as minus commutator of a comma b, right? From, definition of commutators, right? Is that clear? So, yeah. All right. So then then we see that what I'm doing here is only this part, a plus ib, a minus ib. It is equal to this, and therefore your real relation is if you want to write it this way, you can write that a plus ib times a minus ib is equal to this plus I times this commutator. What makes sense? So now that's complete. That's a correct relation now, right? And this is true both for numbers and for operators now, right? Because for numbers this is by definition 0, right? Commutator is definition 0, right? But this is true numbers, operators, and in fact, just to be clear, this is true for matrices. That's what we're talking about here. Yeah. Okay. So now. So let's do one more thing here, and then we kind of finish this up. Just one second. Do I need to sign this? All right, I'll just get the signature then. Okay. Okay.
So straight not to interrupt.
Oh, no problem at
I'll
all.
just
Okay.
tip through American Gold.
Oh, they already did?
Yeah.
So cancel it?
Yeah.
All right, I'll just leave it on.
Absolutely.
And
I just need
sign?
that top copy of.
Alright.
The other ones are yours.
Okay.
They're all set.
Thank you so much.
Yep, good
You
night.
okay?
Oh, yep.
Thank you. All right. So let's finish up this discussion before we. All right. So this is what you get if you choose these operators, and you can see that where is the harmonic oscillator Hamiltonian if I write it this way, right? It's just this part, right? A squared plus b squared. That's your harmonic oscillator Hamiltonian, right? Only that. So then you can write then that the harmonic oscillator Hamiltonian will be, when I say square root, this is what I really mean. So the Hamiltonian is equal to A plus IB, A minus IB minus I times, A comma B, but A comma B for the harmonic oscillator problem is I by 2, right? So you get minus I by 2, and that gives you what? That's just half, right? So that becomes plus half, right? Minus of minus I, so that's plus half, right? Right? So your Hamiltonian, which is your all kinetic plus potential energy and all, is now written like this. And it's even now it's not very interesting. It's just looking, it's a little different. That's all, right? And this A plus IB term, which is, you can see from here, you can construct it. A is so A plus I times B is let's take this quantity out, m omega by 2 h bar, okay? And then we say x plus I. And what will be left out here, and I think I've written it somewhere over there. Yeah. A plus I E. Yeah, I over m omega. So this is when you work it out, it's going to look something like this. A plus IB, and similarly A minus is just is going to be the same thing with x minus I over m omega px. Right? So this quantity, Dirac defines, the two quantities separately. This one as, another operator. You can see now it's mixed up, space and momentum. X and P are mixed up, and it defines this as A, and it will become what we will call as, realize as the annihilation operator. You can write it as small a, sometimes with a hat, sometimes not. And the other will be a complex conjugate of this quantity, and that's A. Oh, sorry, what did I do? A plus IB. No. So the first one is A. And this one is written with a plus, which is, you can think of it, is the Hermitian conjugate, meaning you take transpose if you are a matrix and then take complex conjugate of every term. It's Hermitian conjugate. If you are dealing with numbers, it's just the complex conjugate. Okay, so these are the two quantities, and you can now write, I think I kind of probably have messed up the order here, plus and minus again. Sorry, what's that? Say that again? Yeah, you're saying it's minus half? Yeah, probably you're right then. So let me just say that this quantity, after you work it out, will become A dagger A plus half. This is what it's going to become. And there'll be a h bar omega out, h bar omega out. And what I'm trying to say is, with these definitions, no new physics whatsoever, just redefining operators and saying I'm going to combine it in this way and all that. Right? And I've written this out, and you can. I'll post some of this stuff up as well, and if you have any books, you will always see it in any quantum book. So this is x plus IP, and this is x minus IP. Other things are all coefficients and constants. So you work it out. Okay? So now, what is really interesting about this is that classically, using differential equations, Schrodinger's method, people had already found all this stuff, the wave function and everything. Yeah. So what Dirac does next is he looks at, these are very interesting, things that came out of trying to, write the Hamiltonian in this way. But if you look at the Hamiltonian and say that it's going to act on state n, all right, state n, which is state n maybe 2 or 5 or something like that, right? Then its eigenvalue from Schrodinger's equation, right? Its eigenvalue, and that happens to be what? It's h bar omega. So it's going to act on state n, and its eigenvalue is h bar omega times n plus half, right? Times n. That from me, right? So now you look at this equation and says that it looks like A dagger A is an operator that if you operate using this operator on the wave function or the state of the particle, it's going to detect which state you are in, right away. Right? So this is what is called the number operator. So it will count what's the quantum number. So this is the operator. He realizes that right away by looking at this, and that's obvious from this picture, right? That if you take A dagger A, where A and A dagger are defined like this, combinations of x hat and p hat, and you act it on state n of the harmonic oscillator, you get the number n times the state n. Right? So the number n is an eigenvalue of that operator. Yeah, that's the question.
Is this the same or different than like the creation and annihilation operators that you use like create a site and destroy a site for carry or half wave?
Yeah. So we are building up this thing because the entire creation annihilation operator is based on this idea. So that's where that's where the creation annihilation operator idea comes from. From this sort of picture. And then we are going to build up to that. This is exactly the same as the creation annihilation operator. This, as I mentioned here, is the annihilation operator, is going to lower the state, and A dagger will raise, create state. So we're going to look into that right now. But anyway, this is clear that it pulls out the number of the state, or the quantum number of the harmonic oscillator. And then basically what it's trying to do is say that, but what are these two operators? Do they have any physical meaning? Do they have physical meaning and leading towards this creation annihilation ideas? But what you see is if you do the math, you'll realize that these are not what you call Hermitian operators. A Hermitian conjugate, is not equal to itself, right? Therefore, they can't be, they cannot represent a physical observable. So it cannot do that. If you do the things like A comma A dagger here, if you do this, you find the commutator of these two. What you will find is this is actually equal to 1, and you can kind of show that in 2 or 3 steps. A comma A dagger is just 1. And so that means A dagger minus A dagger A is equal to 1. So that's how they're related. All right, I mean, this will basically we get like a minus times I squared over, something like that. You can. All right, so then what he did was say that if I take just the annihilation operator, which is just A, and I act on the state, the ground state of the system when n is equal to 0, right? I take the annihilation operator, and I act on the ground state of the system. What is this actually doing? So I can write it out. I can write down the annihilation operator, which is all this constant m omega over 2h bar. Then I write it as x hat plus I by m omega. And remember, px is ih bar d by dx, right? Minus. Okay. So you get a plus. Acting on the ground state of the system, right? Does that make sense? Annihilation operator acting on the ground state of the system. Here's the full-blown differential equation. Here's Dirac's notation, right, of creation annihilation. And if you do that for the ground state, which was also known, right? The ground state is known. In fact, the ground state of the wave function is just a plain Gaussian with a constant in front. It's known, right? If you do that, you will get a 0 number, 0. You get a 0. That's what you can plug it in and see you'll get a 0, right? And the solution to that, you can see also that you have a very simple really equation here, which will give you you can cancel this out on both sides, and your equation really becomes d over dx of psi naught is equal to minus x, all the other stuff like m omega over h bar, right? Yeah, m omega over h bar times psi naught of x. So you'll get that, right? It's very straightforward, really. And then you can solve this by taking your psi naught here and taking dx here, right? And you integrate, and you get natural log, and basically you will recover your Gaussian, right? This will become x squared by 2 integral, right? So it will become half m omega square x squared by 2 by h bar omega, right? So anyway, you will recover the whole thing, right? So that's very interesting. It says that this operator is acting on the ground state of the system and giving me the number 0, right? Right? And then you can do the same thing. You can go and operate with this operator on state 1, okay? And what you will observe is it's going to give you the number 1 times the state 0. This is what it's going to give you, right? You can operate with this on, what am I doing here? I'm basically applying the differential form onto the wave function. And saying, what am I getting? I'm getting actually I started with state 1 and I'm getting state 0, right? I act on state 2 and I get, actually this is what I'll get, square root of 2 coefficient times ground state 1. This is what I'm going to get, and so on. You can go A on state 100, you'll get square root of 100 times state 99, and so on. So this is very interesting, right? So this is what he sees, and you can see that by this token, it's safe to call physically this operator as what it's doing is lowering the state of the particle. If it was sitting in some state 1, if this operator acts on it, it lowers it to state 0, 100, 99, 2 to 1, and so on. There's a coefficient that comes with it. And that coefficient, A dagger, if it's acting on state n, is square root of n times n minus 1. That's your relation. That's why it's called a lowering operator or an annihilation operator. Annihilation term will become clear later, because what we'll see is in this number n is a count of how many photons or how many phonons there are. If you lower the number of phonons by 1, you annihilate 1. If you raise it by 1, you create 1. And so this is the raising and lowering operator or annihilation and creation. And exactly in the same way, if you do the same business with A dagger, what you see is the relation is if A dagger, which is the creation operator or raising operator, if it acts on state n, it is going to give you not square root of n anymore, but square root of n plus 1, all right? The next integer times the state n plus 1. It will raise the state of the quantum system by 1 level, just by 1 level, right? So that's how the two look. And this is found just purely a mathematical exercise, right? I mean, even now there seems to be no physical reasoning, but the moment we apply this to photons and phonons, each of these raising or lowering is creation or annihilation of a photon or a phonon. So that's what it becomes when we go there, right? And in fact, this is the idea behind most of quantum field theory today, where you also create electrons at one point in space and annihilate them and let it move. This is the picture also for those things. Okay. So as an example, you can now act with this. You can say, I'm going to first act with A, or annihilation, and then act on creation with a creation operator. So what is that going to do, right? A dagger acting on n, A acting on n will give you what? From here, it's going to give you the quantum number, square root of n, times square root of n minus 1. The state n minus 1. So it's going to give you n minus 1, right? Just that, right? So that's your annihilation operator. But now you have a creation operator acting, right? Creation operator sees first there is a number. It doesn't care about numbers. It just goes through, and so you can slide it over here, square root of n, right? And then creation operator is going to act on n minus 1, right? And when it acts on n minus 1, you can see again what it's going to do. It's going to give you the next integer, which happens to be n, right? N minus 1 plus 1 is n, and it's going to bring you back to n again, right? So it's going to give you square root of n times square root of n times n. So it's going to just give you the number, quantum number, times n. So this is the number counter as we saw earlier, right? When you cascade them this way. Is that, so you can kind of work through this if you haven't before. If you have seen it, this is kind of nice. What if I do this? I flip the two around. So remember, the commutator of the two is actually 1, meaning A, comma, A dagger is actually equal to 1. So which means A dagger is equal to 1 plus A dagger A. So you get 1 plus n, and so on. You can kind of play with all this stuff. Okay, so now I think we're over time a little bit today, so probably we can stop the discussion at this point. But what I wanted to really build this towards is, if I have, all right. So I don't want to kind of get started on that today. So perhaps it's better to. So here's the picture we are going to build this towards. Okay, so. When I have phonons, which is a big thing in transport, right? I mean, that's where most of the scattering and all fundamental limits of transport and all are related to phonons. So I'll have a phonon dispersion, and each of these modes of the phonon will be an harmonic oscillator. It's just like this. And so now the electron will come along and it will scatter with the phonons and it will create maybe 20 of these phonons in this mode. So this is a picture we're going to look at. So electron comes in, interacts, creates phonons. Or it comes in and the lattice is already vibrating, it absorbs them. So it destroys the phonons. So raises or lowers. So, and the number of phonons in each mode is this n we're talking about here. And the last thing is you can completely create, this is kind of one of the interesting ideas, that you can create any state by starting from state 0 for the ground state. You can see, first of all, if the annihilation operator acts on the ground state, you get square root of 0 times something which is indeterminate, but this is 0. Right? So you get the number 0. Everything else, it's not a number, it's a state. Right? But the ground state is just going to annihilate. So if you start from the ground state and you apply A, you go, and there's nothing left, it's 0. But if you apply A dagger, you are climbing. So these are sometimes also called ladder operators. They will go up, A dagger will raise you up, and all that. So you can start from state 0, and to create state 1, you can create once, right? But then you have a little coefficient, you write square root of 1. Right? You create state 2, operate again. But then you have a square root 2 coefficient, and so on. You do that n times, right? And you get a square root of n. You get state n. So you can start from state 0, and you end up with state n. By operating it in this way, you have n times the creation operator by factorial n 0. So you can create it this way. So one of the ways to look at this picture is you start from nothing in the universe and you put particles in by creating them here in this state, in this orbital and all that, and you can build your whole state this way. And the last point, really this is the last point today I want to make, is this has led to a very different way of thinking about quantum mechanics too, because differential equation is one way of looking at quantum mechanics. That's Schrodinger's picture. So you can also think of this picture as, if I have phonons like this, right? I can say I can create my, state of the whole system and say I have, let's say I have 30 or, 20 states of phonons here, right? And I have, 20 states. And I can say what is the n of each state? How many, what state is each phonon in? How many phonons are here? Is it 2? Is it 1? Is it, 0? Is it 30? So I can write those numbers down. Maybe there are 2 phonons in the ground state, 30 in the second state, 20 in the. This is a new sort of writing the wave function. This is not a differential, this is not an equation. You can see that. It's not a Hermite polynomial. It's not a sine function. It's just a collection of numbers, right? And the numbers physically mean these are the occupation numbers. How many of those states are occupied, right? So this formalism is called the occupation number formalism of quantum mechanics. In fact, you can completely not do the differential equation and do quantum mechanics this way. This is the occupation number formalism. And we will kind of go back and forth between the two. For example, you do a tight binding model, you write occupation function. It's very easy to write it this way. You want to solve, Kronecker penny model of a crystal, you do this way, and so we kind of go back and forth between the two. But in modern, high energy physics and all that, this is, used exclusively now for many of these, field theories and all that. And this is the genesis of it. It's just the simple harmonic oscillator, and all of it is built around it. So we're going to look at this sort of occupation number picture, because you can see that occupation number picture is very, at least, easy to write. You can just write it this way. You apply an annihilation or creation. You just take 20 to 19 to 18, or you kind of raise and lower numbers. And that's what your Hamiltonian does. That's what your transport can occur. If this is maybe a site here, that's a site there. If I lower this and I raise that, I have transport now, right? So you can picture transport that way as well, from this sort of picture, which is actually completely analogous mathematically. You can prove through the equation for current we wrote, J from the wave function, but this is slightly different way of thinking about it. So, yeah, okay, good. So let's stop here, and I'll again, you can have the food and all that, and I'll be around for questions for the assignment and other things. All right, so we can stop the recording. One of the things also is we don't